Karunakar sir. Karunakar sir. Sir, please start the session, sir. Please.
Good evening to all the participants. On the occasion of 105th birth anniversary celebrations of great mathematicians Dr. Komargolu Chandrasekharan Garu and the 71st birth anniversary celebrations of our former head of the department, Dr. Nagala Prabhakar Rao Garu, the Department of Mathematics is organizing 1 week International Faculty Development Program on innovative applications of mathematics in association with Institutions Innovation Council. On the first day, Dr. P.V. Sundarananda Garu, Professor and Head Department of Mathematics, Rayalaseema University, Kurnool, has delivered a talk on randomness and essential for security. On the second day, Dr. C. Pavan Kumar Garu, Faculty in Mathematics, Apex Max Excel Center, North Carolina, USA, delivered a talk on applications of linear algebra, matrices, and least squares. On the third day, that is yesterday, Dr. G. Srinivas Rao Garu, Professor, Department of Mathematics and Statistics, University of Dodoma, Tanzania, has delivered a talk on basic statistics and nonlinear optimization using R. For the above 3 days, each session was engaged with more than 700 participants. Now I requested our beloved head of the department, Dr. Kevin Acharli Garu, to give his valuable message.
Dear esteemed faculty members and beloved resource person, Dr. N. Fanikumar Garu, good evening to all. We are all gathered here through virtual mode in the 4th day of our International Faculty Development Program on innovative applications of mathematics. We all know that applications of mathematics with the conceptual approaches definitely enrich the faculty members for enhancing their knowledge in multifarious fields. In addition to it, it also helps us to update existing knowledge in teaching community and create a deeper interest in various fields of mathematics. I am thankful to all of you for your active participation and interest towards enhancing your knowledge. Today, our resource person is Dr. N. Fanikumar Garu, Professor, Department of Mathematics, Vasavi College of Engineering, Hyderabad. He did commendable research on population dynamics under the able guidance of Professor N.C.H. Pattabhramachalu Garu, Professor or NIT Warangal. He is one of my research associates, and together we have made numerous new contributions in the areas of population dynamics, particularly emmensalism and commensalism, under the able guidance of our great guru, Professor N.C.H. Pattabhramachalu Garu, retired Professor NIT Warangal. I am sure that his ability not only captivated our attention, but also deepened our understanding of mathematical modeling and its applications. Definitely, his knowledge has to show significant impact on us. Hence, I feel privileged to have such a good research resource person today with us in this section. Thank you very much, Dr. Fanikumar sir, for accepting our invitation. Finally, I appreciate all our participants for their continued enthusiasm and dedication to stay with us throughout the session. I am sure that today's session will be a fruitful one with a learning experience, both enjoyable and enlightening. Thank you. Thank you, one and all.
Thank you, sir.
Thank you very much, sir, for your valuable message. Now I request one of our staff organizers, Ms. I. Rajeswari, to present a refined profile of Dr. N. Fanikumar Garu.
Good evening, all. Welcome you all to a 1 week International Faculty Development Program on innovative applications of mathematics. I feel it proud to introduce today's resource person, Dr. N. Fanikumar Garu. Dr. N. Fanikumar Garu is a professor working in the Department of Mathematics, Vasavi College of Engineering, Hyderabad. He did his MSc in Mathematics from Acharya Nagarjuna University, Andhra Pradesh during 1998 to 2000 and MPhil from Sardar Patel University, Gujarat in the year 2003 to 2004. He completed his PhD in Mathematics from Acharya Nagarjuna University, Andhra Pradesh in the year 2011. He has published 33 research papers and 3 book chapters in various reputed national and international journals. He delivered guest lectures in NIT Warangal in the year 2011 and 2014 and also presented few research papers in various national and international conferences. One student was awarded PhD under his guidance from JNTU Hyderabad in the year 2022. He is an associate editor and editorial board member for few journals and also completed one 23 project from JNTU Hyderabad in the year 2021. Professor N. Fanikumar Garu is appreciated by one and all with his best way of teaching and good research for the last 2 decades. His friendly nature, good attitude, gentle behavior, research capabilities are additional qualities in him apart from his goodness and rich experience in the field of education and research. Thank you.
Thank you, Ms. Rajeshwari, for your nice introduction about Dr. N. Fanikumar Garu. Now, I hand over the session to Dr. N. Fanikumar, sir. Sir, please start the session.
Thank you, sir. Thank
Sir,
you.
is it audible?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Am I audible, sir?
Yes, sir. Yes,
It's
sir.
audible, sir.
Right. Thank you. Thank you to the authorities of Bapatla Engineering College and head Dr. K.V.L. Acharya garu and the senior colleagues in the departments, Dr. T. Srinivasarao garu, Karnakar garu. And basically, I am the alumni of Bapatla Engineering College. Thank you for giving me this opportunity on the great occasion of birthday celebrations of great mathematicians, Professor Komaravalu Chandrasekharan garu and Professor Nagala Prabhakar Rao garu. He is my HOD when I was in Bapatla Engineering College in 1998 to 2000. I did my MSc. Now, thank you. And this is an international FDP on innovative applications on mathematics. Thank you, one and all. And thank you for giving me this opportunity. Right. Today, my talk is basically on the mathematics behind disease transmission from the basic SAR models to the real world model, the recently corona models. Right. So, in this talk, mainly I'm going to deal with mainly my research is under ecological models and ecology, the predator-prey interactions, and later I moved into an epidemiology model. Now I am going to do some mathematical research on eco-epidemiology model, ecology and epidemiology, both are. Now, today my talk is on disease transmission models from SAR model to real world epidemic models up to corona models, right? So, in this talk, mainly I'm going to deal with the disease transmission model, that means an epidemic model. Mainly the epidemic model, how the disease is going to transform and what are the basic mathematics involved in that model, and how when the disease is transmitted, then the disease is invaded, and up to what time that disease is there in that population, whether the disease become an epidemic or the disease is going to be die out, what are the factors involving in that one, and what are the key parameters what we are going to observe to control that disease. And the most important throughout this session, what are the basic epidemic models and what are the parameters involving in that models, and what are the literature, that means what are the most important definitions and what are the assumptions we are going to take care by developing that particular model, and finally what are the assumptions and what are the conclusions we are going to get from that from that models, and how we are going to develop a new model, and we will see all these things in this throughout this session, right? So mainly I'm going to take some of the slides from the internet because those slides that I inspired a lot. That's why I don't want to change that one. I'm taking from that internet and I'm adding some of the basic things in these my slides. Right. So the mainly if you go to the epidemiology, the epidemiology is a branch of medical science which investigates all the factors that determine the presence or absence of a disease and a disorders. So mainly the epidemiology deals with the diseases present, the absence of the disease, and by this study, it is the study of disease. It is the study of the spread of disease, how the disease is going to spread in a space and time, and that objective to trace factors which are responsible for that or contribute to their occurrence. So, from this study of this epidemiology, so what factors are going to be influencing? Suppose when the disease occurs, when the pathogen enters into the population, right? So, what are the
Panikumar,
factors
sir.
involved? Sir.
Sir, please share your screen, sir.
Sir, already shared.
But actually, it is not visible, sir.
Is it okay?
Yes, sir. Yes, sir. Thank you, sir.
Thanks. In this talk, we are focusing on epidemiology. What is the introduction? This epidemiology is a branch of medical science which investigates all the factors that determine the presence or absence of disease and their disorders. Right. So we are going to investigate the spread of disease. That means how the disease is going to spread with respect to the time and in space in a particular area, and what are the objectives and what are the key factors are going to be involved in that the spreading of the disease, and what factors are influencing on the spreading of the disease, and all these are going to be studied in this epidemiology.
Panikumar garu.
So, sir.
Screen malla share kaaledanడి. మరలా పోయింది స్క్రీన్.
Now it is visible, sir. Thank you, sir.
Right. So the epidemiology research helps us to understand the cause of certain disease or disorder in a larger population. Right. So when we are studying this epidemiology, so the research helps us how the disease is going to be spread and what are the factors we are going to be controlled to control that disease, and everything we are going to study. And for this epidemiological study, there is a lot of mathematics involving in this epidemiology. And for that mathematical insight into this epidemiology, the books are the famous books, and there are so many books are there, but the most important books are this is History and Odo Reichman and Maya Marcheva, and Fred Brar is also another book. It is by Springer Publications, and everything is going to be involved in mathematics because in the recent corona models also, so many mathematical models are involved, and they are going to taking that mathematical models, and they are giving the conclusions every day. What we observed in the last 5 years back, at the corona time, and they are doing that mathematical models, and they are giving the information, everyday information what we observed in the at the time of corona, right? So the next one, before going to start the history, so where it starts, and it starts from Hippocrates, and later on the various mathematics in 16th century it is started. And here the Daniel Bernoulli is the he started some mathematical insight of these epidemiology models. Right. So before going to this actual epidemiology, we have to learn some basic terminology. That is very, very important. So we will see this terminology and everything, the detailed explanation in the later slides. Here mainly we are using this terminology. That means whether an individual person, we call it as a susceptible. Susceptible means he is ready to attack that disease. Then he is called susceptible, catch that infection. And whenever the pathogen enters into that one, then immediately, yeah, exposed. This is one of the important. We will see that one. So that exposed means that susceptible person is infected but not infectious. That means the symptoms are not appearing up to some time. So that period that from susceptible to that exposed, that period, that is called also called the latent period. So we'll see that one also. And the most important, that one exposed. And whenever the infection occurs, then that people are called infectious people. So actively spreading the infection, and that means they are ready to spreading the infection. That means when they are contacted with the susceptible people, then they are going to be infected. And after that, these are the standard notations and basic terminology whenever you are going to learn these epidemic models. And R means the recovered. So whenever the infection is there, due to the immunity or the vaccination or something, then the people may be recovered. And again, those people can be get into the susceptible population. And then N is the total population. The total population is all these are individual populations. So susceptible, exposed, and infectious, and recovery population. So these are the parameters we are going to study whenever we are doing the epidemic models. So the first one is the most important, which is the transmission rate. So that means the rate at which the infection spreads from an infected people to other, and the recovery rate, which is denoted by some gamma, the rate at which the infected individuals recover, that is called the recovery rate. Incubation rate at which exposed becomes infection. This is called the incubation period, because when we observed at the corona time, he is in incubation. So that means some 1 week is incubation period. That period, which is called from the susceptible, whenever the infected people contact that susceptible, then they are exposed to that one. So that exposed time. So whenever the disease, that means the symptoms didn't appear at that stage, then that is called the incubation period. And these are the natural death rate and birth rate. These are called in our next slides. These are called vital dynamics. So vital dynamics means we are taking the natural death rate and birth rates. So in sometimes we are not going to take in some of the models, we are not considering this natural death rate and birth rates. Without these two are called the vital dynamics, and we are not considering in some of the models, right? And the next one, the continuation of this one. Here, we are going to analyze these models. We are all these models are nonlinear models. So we are going to make them as a linearization at some equilibrium points, an equilibrium point at which the derivative becomes zero. So the main important equilibrium points in these epidemic models, because we are observing so many equilibrium points when in a prey-predator interactions, but in the epidemic models, we are concentrating on most important equilibrium points. One is the DFE, this means disease-free equilibrium point. This is very, very important equilibrium point where there is no infection. So we are considering that an infection is zero. Then that equilibrium point, which is called the disease-free equilibrium point, and endemic equilibrium point, that means the infectious persists. So that means I is not equal to zero. And the most important, the key parameter and the key factor throughout these epidemic models, which is called R naught. So that is the basic reproduction number. So we are going to give the full clarity about this R naught, that means the basic reproduction number, and how we are going to calculate that one by taking one or two models in our following slides. This is the central part of the epidemic model. Depending upon this value of R naught, we can decide the given the particular disease is going to be epidemic or endemic, or that going to be die out. So the basic reproduction number, the definition is average infections caused by one infected person. That means when the person is infected, now he is ready to infect to the other people. Then what is the average infections? So we will see that one. Then the another one is force of infection. That means rate at which is susceptible becomes infected. So whenever the infected person is going to be contacted to the susceptible person, what is the force of infection? And this is the herd immunity. So we heard this one. We heard this definition herd immunity at the time of Corona. So we'll see that one. And here, this is another one, the incidence type. These are the important. That means when the susceptible and the infected persons are interacting in different ways. So mainly in our epidemic models, we are using two types of interactions. One is mass action incidents. That means the susceptible person infected contact to the infected person, and there it is proportional to that constant. Then it is beta si, and the standard incidence is beta si by n. We will see the clarity of this incidence types in coming slides. So these are the basic terminology, and next one, some of now here. So in the previous slide, we are using some susceptibles, exposed and infectious, recovered, and what is the total population, what is the transmission rate, what is the recovery rate, what is the incubation period. So by observing all these basic terminology in models, now we are going to enter into the epidemic in a closed population. That is very important. A closed population. What is meant to be a closed population? Most of the epidemic models we are doing under a closed population. In general, population of course show demographic turnover. What is meant by meaning of demographic turnover? The demographic turnover means some individuals may birth or disappear due to their death, or by taking the immigration or migration. These are all under demographic turnover. That means the natural death occurs. That means their birth occurs, and due to the population migrating from one place to another place and immigrating from one place to another place, all these are called demographic turnover. Such a demographic process has its characteristics time scale. So for humans on the order of 1 to 10 years, suppose if you take 1 to 10 years time scale, so has some demographic characteristics. The time scale at which an infectious disease sweeps through a population is often much shorter. Suppose if you take an influenza, so the time scale is some weeks. So in such case, we choose to ignore the demographic turnover. Suppose if you take an influenza models or something, so we are not taking that demographic. That means some small time scales. We are no migrating, no immigrating, no deaths, no new births. So we are turn off that demographic and consider the population. That population. So whenever you are turning off that demographic factor, then that population which is called a closed population also means that we do not pay any attention to immigration and immigration. So that is the most important. So for a models like that, we are not taking that demographic. Then that population, whatever the population we are using in that particular model, that population is called a closed population. Most of the epidemic models we are considering under a closed population. Consider such a closed population and assume that it is in the sense that it is completely free from a certain disease causing organism in which we are interested, right? So whenever the disease occurs, we are not taking that demographic and we are going to take that population as a closed population. Assume that in one way or other that the disease causing organism is introduced in at least one host, right? So that means whenever we are studying the epidemic models, the host get one disease, then we start the epidemic models. Here, we are going to answer three most important questions in these epidemic models, right? Can this cause an epidemic? So whenever the pathogen enter into the closed population, then the disease comes. Now, can this cause an epidemic? That means the disease is going to spread and it becomes an epidemic disease, or that disease may be died out. The next question is, if so, then it is an epidemic disease, then it is spreading throughout the population. If so, with what rate does the number of infected hosts increases during the rise of an epidemic? So when the pathogen or when the disease enters into the host population, then if it becomes epidemic, then what is the infection? What is the rate of the infection? What is the number of infected people during the rise of that epidemics? That is the second question. Then the third question is important. What proportion of the population will ultimately have experienced infection? So finally, how many number of populations are infected? So we are going to answer all these questions whenever we are going to study the epidemic models, and when we are forming an epidemic model. So we are going to answer all these questions. So before going to answer these questions, we have to study the basic methodology. That means already we studied the basic terminology of some of the terminology. What are the susceptibles? What is meant by an infected people? What is meant by an exposed? What is meant by a force of infection? So all these are some terminology and basic methodology. The epidemic in a closed population. In order to answer the above, whatever the three questions, that means whenever the pathogen enters into the population, that closed population. So these three questions, when the can this cause an epidemic? The disease, whenever when the disease enters, then questions when the right. So what proportion of the population will ultimately have experienced infection? Right. So now, before going to answer that question, we have to study some basic methodology. That is, we are under a closed population. Right. Sir, am I audible, sir?
Yeah.
Sir, am I audible?
Yes, sir. Yes, sir.
Right.
Audible, sir.
Right. So before going to that one, we are going to study the basic methodology. For many disease transmissions can take place when two hosts contact each other. So how the disease is going to spread? The disease is going to be spread. That means spread means the transmission of a disease from one person to another person when two hosts contact each other. Where the meaning of contact depends upon the context. Think of mosquito biting man for malaria, sexual contact for gonorrhea, sitting in the same street car for influenza and tuberculosis. So these are all the contacts between the two hosts. The contact may be whatever, right? When the human contacting. So when we are observing at the time of corona by shake hands, the airborne so all these are contacts between two hosts, then the disease transmits starts. Sometimes the contact can be little bit vague. For fungal plant disease transmitted through a transport of spores, so some contacts may be little bit vague. So here we are going to three steps to protocol for all these this one epidemic models. First one, to model the contact process. So first we are observing what is the process of contact between the two hosts. So we have to follow these three protocols when we are developing a mathematical model. The first one is to model the contact process. What is the contact process? And to model the mixing of susceptible and infectives, that is, to specify what fraction of contacts of infective are there within the susceptible, given the population composition in terms of susceptible and infectives. So, to specify the probability of contact between an infective and susceptible, actually, which can lead to the transmission of disease. So we have to follow these three protocols to develop a model. The first one is what is the contact process between the hosts. So the second one is the model to model the mixing of susceptible and infectives, and what is the probability of contact between an infective and the susceptible. So what is the rate? That is the transmission disease, right? So mainly we are going to be a compartment models. The most important whenever we are observing the epidemic models in a closed population. So the compartment models. What is meant to be a compartment model? A compartment model is a type of mathematical model described by a set of mathematical equations which explains how individuals in different compartments interact within a population. So how we are interacting the population, how the people, how that we are going to take the population into different compartments. A compartment model is a type of mathematical model. That means each compartmental model, which is each compartment is described by a mathematical equation. How individuals in different compartments interact within a population, how they are interacting within that compartments. Every individual in each compartment are assumed to be as all the other individuals in that compartment. So every individual in each compartment are assumed to be same as all other individuals in that particular compartment, right? The compartments of the model can either flow between each other. That means here, what is meant by a flow? So here we are going to take a susceptible compartment people. That means a susceptible means they are ready for the infection whenever the infected people is going to be contact. And what is the flow? Here the flow means whenever the susceptible people is when the disease enters or disease the attacks to the susceptible people, then the flow is like this. Then he is going to be exposed. After exposed means up to some time the symptoms are not appearing. After some time, this exposed becomes an infected. So after this infection, then the flow becomes recovered. Recovered means with the immunity, he may be recovered. And again, he is going to be get into the susceptible population. Or maybe at sometimes that means due to infection, the death may be possible. Or by taking the vaccination, he may be recovered. Or with the immunity, he may be recovered. So all these, this is nothing but the flow. So whenever the susceptible people is, he is going to be exposed first, and then that flow becomes infected, and then infected becomes recovered. So the compartments of the model can either flow between each other. That means, for instance, live individuals can flow to a dead compartment with a certain rate, which is 1 by average lifetime. We will see that one. Or they can interact. For instance, if you are observing an ecological models where a predator eat prey, the prey does not flow into the predator class. So because the preys are at one place and predators are at one compartment, so prey does not move into the predator compartments, right, into the predator class. But the number of predations that can survive is related to the number of prey available for them to eat, right? And the survival of prey is obviously related to the number of predators around to eat them, right? So like that, the compartments, the individuals, so the flow is like this. Then again, the flow is not coming back. Only the after the flowing, after recovered, then it comes into the susceptible compartment. So a compartment model, which is a type of a mathematical model which explains how individuals in different compartments interact within a population, right? So here are the compartment models, and here are the basic compartment models. The rates of flow between compartments and interaction rates between the compartments are known parameters of the model. These are the most important one when the epidemic models. So these parameters will decide how the infection is going to be from one compartment into another compartment. What is the force of infection? All these are by the parameters. So the rates of flow between compartments and interaction rates between the compartments are known as parameters of the model. During the formulation of these models, the population under study is divided into different mutually exclusive classes. This is very, very important. So all the compartments are mutually exclusive classes. That means their intersection. Already we studied, we know that one mutually exclusive classes. During the formulation of these models, the population under study is divided into different mutually exclusive classes. That means a susceptible class, or infectious class, and a recovered class, depending upon the type of the disease and the condition, because these are varying depending upon the disease of the model. So here, the basic models, there are some standard mathematical models which are generally used and used to understand the epidemic and the disease. These are the basic standard models. So the first one, if you are observing here, this is an SI. SI model. S is the compartment where the susceptible people are there, and then with this rate beta, the susceptibles are going to be interact with this infected. So that means the force of infection, that is beta SI. This is already we studied in the previous slide how because in one of the question already, if you are observing, we are having three questions already we studied. Can this cause the because here? So to model the contact process, what is the contact process? And here, if you are observing here, that what is the incidence type? So here the mass action incidence type. One is beta SI, and the second one is the standard incidence type. Right. So here, this is the mass action incidence type. And here, if you are observing here, the susceptible class, and this is the force of infection beta. So it which interacts with these infected people. And whenever the infected people, after some immunity or something, vaccination or something, they are recovered. This delta is called the recovery rate, and again, this infected people is going to be into the susceptible class. So these are the basic models. This is called an SI model, and this is called an SIS model. So compartmental model consists of two compartments. So basically, the susceptible compartment and the infected compartment. Right. So SIR model with vital dynamics. This is the most important and basic epidemic model, which is called an SIR model. The SIR model, we are having three compartments in this model. One is the susceptible, infected, and recovered model, proposed by Kermack and McKendrick, is one of the simplest and efficient epidemic models. This is a very popular model. During formulation of this model, the total population, that means the total population is N. We are considering it as N, the total population. The total population is divided into three mutually exclusive compartments. So one compartment, which is called the susceptible population. The susceptible population, it comprises of those individuals which can contract the infection and can become infective compartments. So they are going to be get the contact whenever they are going to be infection, then they are going to be in an infective compartment. So which can contract the infection. Now the infective population, it includes those individuals which are capable of transmitting the disease to susceptible population, right? So already in the susceptible population, they are ready to infection, and whenever they are infection, they are coming to the infected population compartment. So whenever they are infected, then they are ready to give that infection to the susceptible population. And the third compartment, which is the removed population, this compartment includes those individuals which having contracted the disease, have either died or become permanently immune once recovered. So in this compartment, there are two things are going to be happen. So whenever the infection, they are coming to this one in the removed population or the recovery. And the removed population means they are going to be died, or with that immunity power, they are become permanently immune the once they recover or have been isolated. Thus, they are unable to further transmit the disease. So in this compartment, the individuals, they are not able to transmit the disease. So these are the three compartments in this most important SIR model with vital dynamics. What is the meaning of vital dynamics here? Here in this vital dynamics, we are not going to take any natural death rates and natural birth rates. We are not taking that one. So because whenever the population is there without disease or when the disease occurs or without disease, some naturally they are having the death rates and birth rates are going to involve. So those are called the vital dynamics. Already we discussed earlier. So this SAR model we are taking without vital dynamics. Now, what are the equations involved and what is this model we will see. Now, before going to model that one, we are having some assumptions which are involved in the formulation of the model. What are the assumptions? The total population remains constant as it does not consider immigration or immigration, and neither birth or nor death in the population. These are called the vital dynamics we are taking. The total population is always constant. That means whatever the population susceptible and infected or recovered, then the total population N is always S plus I plus R. We are not taking the birth and deaths or immigration or migrations, right? The number of susceptible individuals who contracted infection from an infected individual per unit time at a given time t is directly proportional to the total number of susceptible individuals with the proportional coefficient that is called the transmission coefficient. So what is already we discussed earlier, the transmission coefficient is beta. What is that transmission coefficient? The number of susceptible individuals who contracted infection from an infected individual. That is also called the transmission coefficient, or it is also called the force of infection. Beta is called the force of infection. That means when the susceptible individual who contracted an infection from an infected individual. Right. And another one is the individuals from the infected. Hello. ఇది పోతే అది పోతుందని చెప్పి నేను కట్ చేస్తాను. సార్ 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 ఈజ్ ఇట్ ఓకే నౌ సార్?
లేదు, స్క్రీన్ షేరింగ్ పోయింది అసలు.
షేరింగ్ పోయిందా సార్? ఇది మోడ్ లో ఆ మోడ్ లో పెడితే షేరింగ్ పోతుంది సార్.
కొద్దిగా లెటర్ సైజ్ పెంచండి సరిపోతుంది.
అలాగే సార్, అలాగే సార్. ఓకే సార్.
ఓకే ఫణికుమార్ గారు, ఓకే
సార్. ఈజ్ ఇట్ ఓకే?
ఓకే అండి, బాగానే ఉంది
సార్. So these are the assumptions we are taking because in the previous slide we are taking that SIR model, and this SIR model having three compartments. One is susceptible and infective and removed population. So when we are going to model, we are going to take some assumptions. So the first assumption is the total population remains constant, and the force of infection, that means the transmission coefficient rate, which is called the beta. The individuals from infected compartment are moved to recovered. That is the recovered compartment. Whenever the infected people are there, those individuals from infected compartment are moved to recovered or removed. That means due to death, they are removed from the total population. Recovered compartment at the rate proportional to the number of infected individuals. That means the number of infected individuals, how many individuals are going to be recovered. So this gamma is called the recovery rate coefficient. So these are the, it is also assumed that the recovered individuals gain permanent immunity. So they are having permanent immunity and they are not going to expose it again with the disease. So these are the assumptions we are following whenever the epidemic model, and particularly this SIR model. So three compartments, one is susceptible, infected, and recovery. And these are the assumptions. And based on all these assumptions, now we are going to form a SIR model. So what is this SIR model? This, based on the above assumptions, the model takes the following form, and dsdt is equal to minus beta si. So this is called the SIR model. S is a susceptible compartment, and I is an infectious, and R is the recovered. So beta is going to be the force of infection. So the negative sign indicates from the susceptible people, they are going to be infected. That means the rate of change of susceptible. So it depends the growth rate of the susceptible people depending upon this minus beta S sign. The negative sign indicates the rate of growth decreases. This negative beta, that means the susceptible population is removed from this compartment and they are going to be infected and they are going to join in this infected compartment. Then this whatever that means the transmission rate, which is called the beta. So where that population is going to be added in this infected compartment, that means DIDT is equal to beta Si. So whenever this infected compartment, then with that immunity or something, they are going to be recovered. So this gamma is called the recovery rate. So therefore, the growth rate of the infected compartment, which depending upon this one beta Si, and they are going to be recovered, and those population are maybe removed from these infected compartments. That means gamma I, and whoever this removed these people, then those recovered people are going to be joining this recovered compartment. So these are permanently immune. So if you are observing this, the total population, if you are adding this one minus beta Si plus beta Si minus gamma Si plus gamma Si, all are cancelled. That means dsdt, didt plus drdt, which is equal to 0. So the total population is always constant. So this is the flow diagram of SIR model without vital dynamics. That means here we are not considering any death rate and any birth rate. We are not taking any migrations or migrations. So without vital dynamics, this is an SIR model. And the next one. So these are some of the modified SIR model. So the next one is SIRS model. That means where in that previous SIR model, we are having some immunity is there, that permanent immunity, some of the people. So after recovery, they are not going to join in that again, that is susceptible. And we are having another developed model and modified SIR model, which is SIRS model, a susceptible compartment people, and which is transferred with this rate of transmission beta Si. So infected, and then this from this infection rate of that recovery is gamma I. After the recovered, again, they are going to join this susceptible with this recovery rate delta. And this is SIRA model. So another modified model of SIR. So susceptible people with this transmission rate beta, then they are going to be infected. Infected people with that recovery rate will becomes recover. And after that recovery, without having some immunity and everything, again they are going to be get infected. And again they are going to join in this. This is delta, and this is an infected compartment. And SIR model with vital dynamics. So we are having this is previously we are not taking here, there is no vital dynamics. Here, SIR model with vital dynamics means in this compartment, there is a birth rate. Some new births are always joining the susceptible people with the birth rate B. And from this S, there are susceptible, the natural death rate of these people, which is called mu-S. This is the natural death rate of susceptible mu. And beta Si, this is generally SIR model. beta SA, this is the transmission rate from susceptible to infected. And for this, the natural infected people, this is called mu I. And from this recovery, which is called mu R, this is the natural death rates of from the compartments of SIR. And new births are going to join this susceptible people. And beta SA, beta is the transmission rate, and gamma is the recovery rate, right? So this is the SIR model with the vital dynamics. These are the modified SIR model from the basic SIR model, SIRS, SIRI, and SIR with vital dynamics. All these are the each compartment already we discussed in the previous slides. Every compartment, depending upon the flow, depending upon the mathematical equations, what that mathematical equations already we described in this SIR model. That means dS by dt minus beta SI, dA by dt beta SI minus gamma A, dR by dt is equal to gamma A. So with the same mathematical equations, we can form this SIRS and SIRI and SIR models, right? Now, so if we are observing some mathematical calculations and everything, these are some graphs, how the susceptible people are. Previously, the susceptible people, this is the orange color graph. So the susceptible people starts from 1,000 susceptible people whenever they are infected, and slowly that is going down. So that means the infected rate is initially, which is 0, and the recovery rates are 0. So gradually the infection going to be peak at this position. And whenever this one is, then it is going to be die out because with the infected class rises, reaches peak, and then falls. Recovery rate from this, whenever it falls, then immediately the recovery rate is increasing, and eventually the infectious dies out because enough individuals have left the susceptible people, right? So these are some by using the parameter values and everything. Finally, we are concluding this one. And this is somewhat SI model, right? So previously we are observing SIR model, the various modifications in SIR model is SIRI and SIRS and SIR model with vital dynamics, and another most important model, and they are introducing this one class which is called the exposed population. That is very important, and this is very popular model which is called SEIR model without vital dynamics. That means there is no natural death rate and birth rate. So this is most important development of that SIR model, exposed population. Already we discussed what is meant by an exposed population. The exposed compartment consists of population that is exposed to the vital event, and for example, the total population in case of deaths, the legally married population in the case of divorce, and so on. In the case of disease modeling, exposed population refers to the fraction of population which is infected by the disease but not yet infectious. So recently we observed that the corona models and everything, whenever that disease attacks, immediately we are not going to get the symptoms. After some time, we are going to get the symptoms. So that means already that susceptible population is exposed, and some period of time, the symptoms is going to be appear. During the formulation of SIR epidemic model, it is assumed that susceptible individuals immediately become infectious once contracted infection. That is the case in SIR model. Whenever the susceptible population is going to be contact with infectious people, then immediately that infection immediately gets to the susceptible people. Such individuals then directly move from susceptible compartment to the infected compartment, then S2I. But for some diseases like tuberculosis, this is not true. Hence, SIR model is not a suitable model in such a scenario, like our corona models also. For some diseases, immediately the susceptible people are not going to get infection. Immediately, we are not going to get some symptoms. To include this situation, SIR model is modified by adding another compartment of exposed individuals. The members of these compartments are infected, but not infectious. That is, they are not capable of spreading the infection. Up to some time, they are not capable of spreading that infection. So that class is called an exposed class, and this is so. In terms of the equations, the SEIR model without vital dynamics is expressed as like this. This is the flow diagram of SEIR model, the susceptible class, and the exposed class. And from this exposed class, that is the exposure rate, and they are going to be an infected class, and from infected to recovery. So ds by dt is minus beta si, and this is de dt. This is beta si. Here it is beta si minus sigma e. This is the growth rate of this infection is sigma e minus gamma e, and dr dt is which is gamma I. So again, so we can modify this SEIR model, the flow diagram of SEIR model without vital dynamics. And again, after that means that recovered class with the immunity or something, again they are going to add into the susceptible population. That is called SEIRS model without vital dynamics, right? The next, the important terminology in mathematical epidemiology, already we discussed it. So in case of infectious disease, the contact with an infectious individual plays an important role in transmission of infection. Whenever the infectious disease, the contact with an infectious individuals plays an important role. What is the transmission of infection? Contact rate, the total number of individuals contacted by an infectious individual per unit of time is known as contact rate. So per unit of time, how many people are going to be contact with that infection people? In general, all contacts with infectious individuals do not result an infection. Then another one is adequate contact rate. Suppose that the probability of infection by each contact is beta naught, and U of n is the contact rate. Here n is the total population size under consideration. So the function which is defined as the product of beta into UN. Already we observed that beta S. So that beta Si. So that means that is the susceptible population contact with the infected people. That is beta Si. That product beta into U of n gives the adequate contact rate, which describes the infection strength of the infectives. So how much this contact? So which depends upon, that is also called the force of infection. During the formulation of the compartment epidemic model, the population is divided into mutually exclusive compartments. Among all these compartments, diseases are transmitted only to individuals belonging to susceptible compartment when they come to contact with the individuals of infected compartments. That is, so that's why we are taking that compartment model. So what is meant by infection rate? The infection rate, if the total population is n, then the fraction of the susceptible in the population size. So what is the fraction? The total number of susceptible by the total number of the population. From this, we can obtain the mean adequate contact rate of an infected individual to a susceptible as this is adequate contact rate beta naught un into S by n. This is called the infection rate. So what is meant by infection rate? It is the mean adequate contact rate. This is the basic terminology. Then, so another one is the incidence rate. The total new infectives infected by all individuals in the infected compartment per unit time, it is beta naught UN SI by N, which is called the incidence rate. There are two types of, already we discussed in the previous slide, there are two types of incidence rate. One is bilinear incidence, which is also called mass action incidence, and the second one is the standard incidence. So if the contact rate is proportional to the total population size, that means U of n is directly proportional to n. That means U of n is equal to some k times n. The incidence is beta Si. So where that beta is equal to beta naught k. So that contact rate that U of n is directly proportional to the total population. So where k is constant, that incidence beta Si is called bilinear incidence, or it is also called mass action incidence. Another type of incidence, which is called standard incidence, if the contact rate is constant, in this case, the incidence becomes beta Si by n, where that beta is equal to beta naught times C. So the contact rate is constant. So this type of incidence is known as the standard incidence, right? So these are the terminologies, what is meant by incidence rate. So incidence rate we are going to take in two forms. One is the bilinear incidence and the second one is the standard incidence. And in the most of the epidemic models, we are considering the bilinear incidence, or in some of the epidemic models, we are taking the standard incidence. And this is the average lifespan. Already we observed this average lifespan in this model. If you are observing this dn over da, which is equal to minus mu n, which is law of natural growth we observed in this first order differential equation. So where a represents the age. So if you take the probability density function and that one, so the standard incidence rate, which is called the average lifespan, which is called 1 by the natural death rate. Mu is the average death. So 1 over mu is the average lifespan. So the inverse of the probability transmission of infection is known as average infection age. So it is also called waiting time. That means up to that time, the symptoms are not appearing. That is very important. So whenever the infection is transmitted, that means that waiting time is there. That is called average infection age. Up to the time that infection appears. Now here, in this epidemic models, all these are terminologies, very, very important terminologies. Without knowing, we cannot do analysis of that epidemic models, right? So what are the infection rate? What is the contact rate? What is the force of infection? What is the latent period? And everything terminology. That terminology is very important whenever we are doing epidemic models. And what are the basic epidemic models and what is the flow? Everything we have to observe, and what incidents we are going to consider, and what are the whether we are depending upon that disease we are going to consider that vital dynamics or not. Everything by all these assumptions we are going to form a mathematical model, that means an epidemic model, right? So in that terminology process, the most important terminology in that epidemic throughout the epidemic disease, this is called the basic reproduction number. A very, very important reproduction, very, very important thing, which is called a basic reproduction number, which is denoted by R naught. Depending upon this value of R naught, the people can decide whether the disease is going to be die out or the disease is going to be epidemic. What is meant to be a basic reproduction number and how we are going to calculate this basic reproduction number whenever the model is there. We will see that one. So what is meant by a basic reproduction number? If you are observing this one in this figure, if you are observing, so this is the blue color man, which he is an infected bee. So all susceptibles then. So he is going to be infected 2 persons at a time. So the average number of secondary cases, the definition of basic reproduction number, the average number of secondary cases produced by a typical infected, assumed to be an infectious person, typical infected individual, entire life as that means that means up to that infection period, and how many people he is going to transmit it that disease when introduced into a population of susceptible is called a basic reproduction number. So if you are observing if you go through this one, suppose if it is R naught is expected number of secondary infections caused by a single infection individuals introduced into fully susceptible population. And this one, so if you are observing graphically, see here. So if you are observing here, this is the infected people. At a time, he is going to be infected to 2 susceptible infection. And from this infected, another 2. This is another 2. This is another 2. This is another 2. This is another 2. Here, that means R naught is equal to 2. So the basic reproduction number, which is the average number of secondary cases produced by a typical infected individuals. That means when we are taking this average number, this is 1 infected at a time, he is 2 by 1, and here it is 4. In the second stage, 4 by 2, which is equal to 2. In the third stage, which is 2, 2, 2, 2 again. So 8 by 4. Then from the third stage to this, from fourth stage to third stage, again it is 2. And like that, we are calculating what is the average number in the he produced. Then that is called R naught. So here, in this case, that R naught is 2. So if you are observing this one, this R naught, the basic reproduction number, from this definition, it is clear that R naught helps us to determine the future course of the infection, how the infection is going to be become. So furthermore, it is also evident that each infected individual produces on average less than 1 infected individual. That is that is R naught. So he is going to produce less than 1 individual. He is going that infection. Thus, in this case, we can predict that the infection will die out. So we observed in Corona situation every day. We are observing the newspapers and the channels. What is R naught? What is R naught? What is R naught? So this is the R naught. On the other hand, if R naught is greater than 1, the pathogen is able to invade the susceptible population. The pathogen is increasing. That means the disease is going to spread. So if you are observing the literature, if you are observing, so this is if you are observing for some of the disease. So if R naught value less than 1, then that infection dies out. That is some Ebola. For this disease, if we are calculating, R naught is equal to 1, endemic flu levels. And for this COVID-19 and smallpox, R naught is equal to 2. And for that COVID, this means the original first span of COVID, and this one R naught is equal to 3 for measles. That R naught is equal to 12. That means that 12 is nothing but from an infection, immediately he is going to spread 12 members at a time. That means how much that disease is going to be transmitted. So this is R naught, which is greater than 1. Infection can invade in the population. If R naught is less than 1, then the infection will die out. Suppose if it depends upon R naught. If R naught is equal to 1, then this is the seasonal influenza what we are getting in a seasonal time. So after time, sometime the infection is going to be dies out. And if R naught is equal to 2, this is early COVID original strain. So for a smallpox also R naught is equal to 2. So if R naught is equal to 3, then what is going to happen? So very rapid spread, highly contagious disease. So this is a SARS-CoV-2, and mumps also a disease which are having a basic reproduction number R naught is equal to 3. So how this the basic reproduction number is very important, right? So there are so many methods to find out the basic reproduction number for a given model. And here we are the most famous method, which is called the next generation method. So by using this next generation method, we are going to find out the basic reproduction number. The next generation method is frequently used to compute the reproduction number of disease below. We give a brief description of this method, and straight away I'm not going to explain this method directly. Through an example, I am going to explain this one. So a basic reproduction number, how you are going to calculate, this is very important. So here I'm considering this one SIR model. This is one SIR model. Here with demography means we are going to take birth rates and some death rates. So if you are observing this one, which is DS over DT, which is mu n, because this is per capita 1 by n. So ds by dt is equal to mu n. This is the natural death rate, and beta si. This term represents the susceptible people contact with this infected person. This is beta si by n, and mu s. This is also the natural death rate. And here di by dt from this beta si by n, this is from susceptible population. They are removing from the susceptible population, and they are going to, here it is not minus, it is plus. So beta si by n minus gamma I minus mu I. So minus gamma I means this is the infection. They are recovered from this infection. And here minus gamma I, and this minus mu I, which represents that means they are going to natural death. And whenever this is minus gamma I, this is the infected people, and they are recovered, and they are removed from the infection compartment, and they are going to join this recovery compartment, that is called gamma I. So what is this mu R? This is the natural death rate from that recovery compartment. Right. So this is focus. This is SIR model. From this, what we are going to observe, we are focusing to find out the basic reproduction number. So for finding the basic reproduction number, we are going to concentrate on two things. The basic reproduction number we are going to find out at a disease-free equilibrium point. So at disease-free equilibrium point, we are going to find out the basic reproduction number. That is the first most important point. Right. So we focus only on the infected equation because R naught depends only on infection dynamics. That means we are going to focus on disease-free equilibrium point, means where at that point the infection becomes zero. There is no infection. So at that point only we are going to find out the basic reproduction number. So that is the disease-free equilibrium point. What is meant by a disease equilibrium point? Where that infection becomes zero. So by taking that infection zero, then if you are observing this R, then this R becomes I becomes zero. Then this I becomes zero. So ds over dt is equal to zero. By calculating that, because this is the equilibrium points calculation. So this is S is equal to N, I is equal to 0, R is equal to 0. This is called an equilibrium point. This point is obtained by taking all the first derivatives becomes 0. That means ds by dt 0, di by dt 0, and dr by dt is equal to 0. So this equilibrium point, because we are mainly in epidemic models, already we discussed in the previous slides. In epidemic models, we are going to concentrate on two equilibrium points. One is a DFE, that means a disease-free equilibrium point, and the second one is endemic equilibrium point, epidemic equilibrium point. Right. So this is we are going to find out a basic reproduction number by using the next generation matrix. So what is meant by a next generation matrix, we will see. So the next generation matrix here, which is called, this is called the next generation matrix. This means Fi of x minus Vi of x. What is Fi of x and what is Vi of x? How we are going to calculate? That is the first one. What is meant by f of x and what is meant by V of x. And after getting that f of x and V of x, and finally we are going to calculate f times V inverse. That is called the next generation matrix. F times V inverse. That gives us the reproduction number. So for this, here in these slides, I given two examples to find out the reproduction number. One example, the model which is having only one infected compartment, only one infection is there. And another model, I calculated that basic reproduction number when the having two infected compartments. That means I1 and I2. So I given this one very clearly in this. I'll share this one. So all these PPTs, and you can do the calculations, and each definition I clearly explained. So what is meant by F? The rate at which new infections enter into the infected compartments. So only the infections enters into the compartment, we are taking it as F. And what is meant by V? V means from the compartment, something are going to be removed with some other things. That means by using the natural death rate or by taking the infection. So they are going to be removed from this compartment. So F means the rate at which new infections enter into the compartment. Here we are taking in the di by dt. If we are observing this model, so in this infection, only this beta Si by n people enter into the infected compartment. From this infected compartment, this minus gamma plus mu into I, they are the people removing from that compartment. That we are going to take it as V. So F defines the rate at which new infections entered into the department. This is the Fi. And we are going to calculate this F at that equilibrium point, disease equilibrium point. So if you put S is equal to N, we are going to get F is equal to Bi. And what is meant by V? The V means rate of all other movements out of the between infected compartments. That means here if you are observing di by dt, the first one is beta Si by 1, we are taking it as F minus this gamma plus mu into I, which are removed from that compartment, we are taking it as V. So the matrix form is F into V inverse. F is already beta and V is equal to gamma plus mu, and F into V inverse, which is called the mu generation matrix, then which is equal to inverse means 1 by gamma plus mu, beta by gamma plus mu. So this is the R naught value when SIR. Suppose when the model having two infected compartments, here if you are observing, so this is the model where in this model we are having two infected compartments, that means I1 and I2, and I1, I2 and I3. If you are observing here, the susceptible population, they are going to be infected. First, they are going to join in this I1. First, they are going to join this I1. Later, they are going to join I2 and I3. So when we are going to find out the basic reproduction number, we are going to take the population, or we are going to take the population. They are going to infected, and first they are going to join in this compartment I1. So if you are observing F here, so you are calculating the first disease equilibrium point where all the infections are zeros. And if you are identifying this f of x and v of x, this is f of s, fi of x minus v of x. So if you are observing here where fi is new infection term that enter infected compartments, and vi all other transmissions outflows. They are recoveries, they are deaths, whatever. So from that model, if you are observing, what is F1 of X? F1 of X means first they are entering into the susceptible people whenever they are infected, then they are entering into this compartment. After this, they are entering into the I2 and I3. We don't bother about that. So we are going to take this as F1 and this F2 and this is F3. There are three F in Fi. There are three things F1, F2, F3. F1 we are going to take this as beta Sn by P1 I1 plus P2 I2 plus P3 I3, and F2 becomes 0. We are not considering because we are concentrating the first infected people joining this I1 department. So therefore, here F1 of X is this one and F2 of X, F3 of X. And the remaining we are going to calculate this V1 of X, V2 of X, V3 of X. That is in the form of F minus V. So if we are observing this one, F minus V, this one, and we are going to form this F1, F1, F2 is already 0, and you make it as in the form of minus V, what V2, and F3 is also 0. You make it as F3 minus V3. So if you are taking that one, this is V2 and this is V3. Now here we are going to take the Jacobian matrix and dou f by dou y, because that is dou f by dou y at that equilibrium point, at that disease equilibrium point. This is F, and the same thing we are going to take the Jacobian matrix of this V, and finally we are going to calculate V inverse, that V inverse, and take that F into V inverse, then you are going to get this R naught value. So here we are following the diagonal matrix. In that diagonal matrix, sometimes we are going to get an upper triangular matrix or diagonal matrix. The diagonal matrix having the eigenvalues are the dominant eigenvalue we are going to take. We are taking it as a spectral radius. And that R naught is nothing but the spectral radius of that generation matrix, new generation matrix. So that means the dominant eigenvalue. That gives us R naught. So that is the basic reproduction number. So these are some of the models. This is a COVID-19 model. So from the literature. So this is the way to find out the basic reproduction number and everything. That's it. Thank you, sir. Hello, sir.
Fanikumar garu, thank you అండి.
Sir, thank you, sir.
Karunakar sir. Fanikumar sir.
Sir.
You delivered a truly useful and enriching lecture on mathematical modeling in epidemiology, sir.
Sir.
Your clear explanation, practical insights, and research-oriented presentation greatly benefited to all our participants. Thank you very much, sir.
Thank you, sir.
Really, it is useful for the researchers. Karunakar sir.
Sir, please, sir. 1 minute, sir. 1 second, sir. Thank you very much, sir, for your presentation. And I now request our Dr. T. Srinivasarao garu to present vote of thanks.
Sir, if anybody is interested to ask question, please ask them to post in the chat box, sir. Otherwise, we may go further.
Because of huge participants, any participant who is interested to clarify their doubts, please come forward to post in the Q&A chat box. Sir will clarify the same.
Fanikumar sir.
Sir.
Fanikumar sir, is it audible, sir?
Clear, sir. It is audible,
Yes,
sir.
sir.
Okay, sir.
Fanikumar sir.
Dear participants.
Sir.
Please send your PPT, sir, because it is useful for the participants.
Sir, there is some
Sure,
question, sir, where we
Sure,
use these practical problems, sir.
Sir. Hello, sir.
Sir, please explain one or two just applications related to that.
Sir, please repeat the question, sir.
Sir, whatever the models we are presenting and whatever the models we are doing right now, these are all present real world problems, sir. We are doing in corona situation or in some of the epidemic models. These are all real world problems, and mainly the epidemic models we are doing with the data, sir. But we are not using that data, but the real situation we are getting only obtained when we are using the real data.
Dear participants, any questions? Dear participants, any
qualitative
questions?
Analysis.
Qualitative analysis. Okay. Sir, there are no questions, sir. Now, please,
sir. Please go ahead, sir.
Okay. Thank you, for and all, for your good response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with a vote of thanks by our co-convener, Dr. T. Srinivasarao garu.
Good evening to all the participants. On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. N. Fanikumar garu, who gave such a wonderful and informative presentation on mathematics behind disease transmission from SIR models to real world epidemics. The session on mathematical modeling in epidemiology introduced how mathematics helps explain, predict, and control the spread of infectious diseases. It begins with the basic concepts like population compartments, assumptions, parameters, etc. Develops classical models such as SIS, SIR, and SEIR and explains equilibrium, stability, and threshold analysis. The presentation blends theory, examples, and visual simulations, provided a comprehensive, research-oriented understanding. In this talk, Dr. N. Fanikumar Garu have discussed the basic concepts, different classical models, and advanced topics in epidemiology. Today's session has been enriched with Dr. N. Fanikumar Garu presentation on mathematics behind disease transmission from SIR models to real world epidemics, which has inspired new ideas among the faculty members and helped to strengthen their research skills. Dear participants, you are all informed that feedback link will be shared both in WhatsApp groups and YouTube link. Please fill the feedback forms. It will open till 7 p.m. today. Thank you, one and all.
Thank you, Fani sir. Thank you.
Thank you, sir. Thank you.
Thank you, Fanikumar Garu.
Sir, thank you, sir. Thanks.
Thank you, Fanikumar Garu.
Sir, thank you, sir. Thank you, sir.